Okay, class, this is going to be the first of the topics that you would be covering. This is, again, we missed first day of class because of the holiday, so I want to make sure you have the material to start on the written homework. This is the deeper understanding. We'll kind of talk through some of these. I also include homework questions in here that I either there's a few, maybe not in this particular one, but in throughout the semester where I actually walk you piece by piece through the whole thing. Other ones I just give you like a skeleton of how to solve it, sort of thing, or how to write up your explanation. And then some I don't give you any help at all because I feel like you should be okay with those, with the material I've already given, and the material in the book. So I wanted to let you know first that that class intro announcement's up with the video for the first week of class and its slides, so you can see that. And then we'll get right into this. We're going to start talking about functions, right? Why not? We're going to start with functions. And my guess is you guys probably already have a pretty good understanding of functions from algebra. We're going to take that a little bit farther, kind of go a little bit deeper. Can I move that out of the way? I don't even know if you guys see that. All right, let's see what happens when I just move on to the next one. Okay, so first, what is a function that is in the way? Cannot. There we go. Okay. And then that should disappear. There we go. Okay. So let's define functions. Oftentimes, you guys have already defined functions as a variable, something in terms of a variable. We're not going to do that because those are very specific cases. We want to look at the broader picture of what a function is. We know a function's a relationship. We know certain things are functions, certain things are not functions. If you think back to in algebra, you might have used the vertical line test, right? That's a nice test if it's something mathematically you can plot. But more importantly than that, it isn't about the mathematics. It isn't about the calculation part of it. It's about the mathematics, the critical thinking. Um, calculation is just such a small part of mathematics, and I know that's the part most people think it is. The reality is we don't, mathematicians as a whole don't do calculations on a regular basis. Unless that's your career choice, they do critical thinking, creative thinking. So thinking about it critically, a function is something from one thing to another, one set of things, maybe. We think about them numerically, but we can also say that it is a set of students to their birthday, right? That would be a function. Each one of you have a very specific birthday. Now, it could be the same. Two of you could share a birthday, but it's also the fact that you only have one birthday. Now, if I were to go the other way, if I was to look at dates and go to students, that may not be a function because if two of you shared a birthday, there's no problem with -2 going to 4 and 2 going to 4 if I square both of them. That's okay. They both give me the same output. They had two different inputs, but they gave me the same output. Same thing if you guys share a birthday. So two of you share a birthday. That's still a function if I go from you to the birthday. If I go the other way, so now I go birthday to you, it may not work because one date might have two outputs. And if an input has two outputs, it's not a function. So we need to define functions better than just input going to output. So in this case, we're going to define them as provisionally. Let A and B be non-empty. No point in looking at empty sets. So these are sets. Uh, and we're going to define a function from A to B, and we're going to write it like f. We're using f because we're calling it a function, A to B, to be a rule that assigns to each element of A, each element in the set A, to go to an element in the set B. It doesn't mean we're using everything in B. It doesn't mean we're using all those elements in that set, but we are going, in our case, every one of you have a birth date. It doesn't mean we're going to touch every day in the year. So it's okay. Uh, so that's provisionally, we're going to take the set A and we're going to call it the domain. We're going to call set B the codomain. You'll notice I'm not using the term range here. A lot of you are thinking, well, wait, the domain goes to range. No, the domain goes to a codomain when we talk in general. When we talk about specific outputs, then we're talking about the range, meaning there's 12 students in the class. If I set all of you to be my domain, but I set my codomain to be any date in a calendar year, so January 1st through 12/31, right? So December 31st. Any date in there, and I put you guys in, any of those dates are my codomain, any one of those. But there's only 12 of you, so that means there's only 12 dates. I'm not actually getting every date. Those 12 that I get are the range. So I want to differentiate what is range and what is codomain. When we talk codomain, we're just talking in general. We haven't figured out what the outputs are. When we talk about range, we know what the outputs are. Mathematically, if we look at, or calculation-wise, if we look at a map of a function that's with numerals, we could get an idea of what that range would be, and we can restrict it. But all the numbers would still be part of the codomain. So we do need to make sure that we differentiate. That's why we're using codomain here. So this means input some element of A, our first set, will give us an output in an element of set B. That is formally a provisional definition. We're going to fine tune that, get a little bit more detailed. Some of the elements of the codomain may not be output of our input, as I said. And all of the outputs of our inputs are considered the range. Why sets? Why are we using sets? Well, you've learned inputs and outputs as numbers rather than sets. An example would be 2 to infinity, right? And you'll see I'm including 2 here. So, and then I give it this nice function that says x such that, and this is set builder notation, and I say x such that x is greater than or equal to 0. So any of those could be x. Using sets allow us to define functions whether the domain or codomain are numbers or not. Again, I did it with people. I had a set of students. I could make that set all GCU students, right? It is still mathematics when we talk about it like this, even though there's no calculation happening. This is where a lot of students are like, wait, I focus in on the calculation. That's what I'm good at. Maybe that's why you chose mathematics. That's fine. But reality is calculation is just a little itty bitty part of mathematics. Most of mathematics is critical thinking and creative thinking. So this idea of understanding what's happening and applying it to all aspects of things. So keep that in mind. When we talk about sets A and B in general, if we consider the database of students at GCU, and we say, okay, well, is this a function if I go from the name of the student to the birth date? And I've kind of talked through that a little bit. Now I've just made my database all GCU students. Do I have to restrict that? No, I could actually say all, meaning all students who were at GCU at any one time. So this does not include students who did not attend GCU or people who did not attend GCU, but it genuinely includes everyone since GCU began in 1949. Everyone who attended GCU is okay to use. Or I could restrict it to just say students that are at GCU currently. I could restrict it to be just like we restrict numbers, we can restrict any set that we're dealing with. From the student to the birth date, that is a function. If I go the other way, Again, thousands of students at GCU currently, thousands of students. It's not a function because I guarantee at least two of them are going to share birthdays. Um, so this is not a function. So we have to think about our domain and think about what restrictions apply. I mentioned some already, like whether we were including all, including alumni, students who had been attending GCU at some point, or if we just want to include GCU students that are active currently. These are all decisions that have to be made. For a function, it's possible that some elements of the codomain are not the output of any input. That's when we narrow it down to a class, right? Our class is only 12 students. It's not likely that you guys are going to share birthdays, though it's possible. You're still limited to only 12. Even if you guys share some, even if like three of you shared a birthday, right? I'm still getting no more than 12, right? So my codomain is very restricted. For a function on the reals, so from the real number to a real number, and you'll notice the double struck R, I tend to use that in my actual physical writing often. So be comfortable with these notations. So from a function on the reals to the reals, if I look at the map for my function as f of x is equal to 2x, this means can I identify a value in the codomain that's not an output of this function? So is there a value in the codomain? Now understand that the codomain here is all real numbers. So is there a value that this can't be? And I'll let you think about that for a moment. And you may think, well, what about odd numbers? 2 raised to a power isn't going to give me an odd number. Since x could be any value in the real numbers, I could technically get a fraction out of this. So keep that in mind. Though there's tons that it couldn't be. The obvious one it can't be, or what I think is obvious, is since 2 is not a negative number, it doesn't matter what I raise it to. Even if I raise it to a negative power or a fractional negative power, I'll still never get a negative result. Also, I will never get 0, right? 2 to any power is never going to give me 0. 2 to the 0 power is going to give me 1. 2 to the negative 1 is a half. So, but I'll never get a negative output. So in my codomain, in my range, this wouldn't go to 0. It would go close, infinitesimally close, but not get 0 and not get any negative numbers. Those are the easy ones. There's actually a few other ones it wouldn't get to in the set of numbers going up, but those are the easy ones. So is there more than one possible domain for this function? So now we're talking about domain, not codomain. So could we use a different domain? And this function is what I'm looking at, f of x. The map is f of x equals x to the squared. So if I think of my domain as real numbers, meaning I could put negatives, I can put positives in there, and I can square them. If I put a negative in there, my codomain is still going to be positive because I'm squaring it, so it's an even power. But as far as the domain goes, could I restrict it? And yes, we could restrict this however we needed to, but I don't have to. Though I would want to be careful using complex numbers. Say I used square root of negative 2. That's a complex number. It's an imaginary number. And that would actually, when I square it, come out as -2. So now my codomain, if I let complex numbers be part of my domain, my codomain could be all real numbers. So we do want to be careful. There are often restrictions. What's a reasonable codomain for this if I keep it in the reals? So if I only put in reals, negative or positive, right? That's fine. My codomain is still just going to be positive numbers. And in this case, because I've said not putting any negatives, zero is neither negative nor positive, so I could still put zero in, which would give me zero as an output. But everything else would be positive. Didn't matter whether I plugged in negative or positive. So keep those in mind. Think about them. Let's talk about the graphs. Um, what benefit do we get from graphing a function? So I'll let you guys think about that for a moment. And my guess is that one of the first things that came to mind was you could use the vertical line test, which is true, though certain things are not easy to graph. Students to birthdays, not easy to graph, especially on the scale that we talk about when we talk about all GCU students. For a class, not a big deal. For all GCU students, that's quite an undertaking. The coordinate plane, you guys, most of you have already taken math history, so I'm assuming you know the rumored tale is that Rene Descartes, while he was sick at one point, started looking at a fly on a wall and trying to map its location. And that is where we get the coordinate plane or the Cartesian plane named after Rene Descartes. Uh, so this is a function. He watched the fly move. That's the legend. Whether or not it's true, we really don't know. I wasn't alive. Um, I'm old, not that old. He he was a famous mathematician. You guys should have learned about him in math history. Those of you that took it with me, I know did. But he did a lot of stuff, mathematically speaking, and he did a lot of stuff before then. He had many careers, many jobs, and he's part of the reason that our notations are the way they are. Um, we consider the Cartesian plane with ordered pairs x, y ideal for graphing because one is the input and one is the output. So that does make things easier. And in this case, we're talking about the location of a fly that can move and land anywhere in a particular region. So again, we're not actually talking about numbers. We're going to use numbers. Numbers will come out of the location of that fly as it moves around on the ceiling, but it doesn't necessarily have numbers in and of itself. So we're going to take that provisional definition and talk about it in terms of graph. So the graph, now let same function, let f be a function of set A to set B. The graph of f is such that for every element A that's in the set A, lowercase a is an element of A, and the f of A, so that would be in B, makes a coordinate plane, makes a coordinate uh, location. So it's in function in that coordinate location. They are a subset of the Cartesian product of A cross B, and the Cartesian product would look something like this. So A cross B would be AB. You'll notice instead of using f of A, we're saying B, and we're saying that A is an element of capital A and B is an element of capital B. You may have already seen this notation. Those of you that have taken linear will see Cartesian products. In other words, a Cartesian product between two sets, A and B, is the set of all possible ordered pairs with the first element from A and the second element from B. This is all possible. This doesn't necessarily mean everything that outputs. So again, we're talking about it in terms of a domain and codomain, not a domain and range yet. Domain and range is when we're very specifically have outputs, specific outputs, not in general outputs. Rigorous definition. So this is our rigorous definition. This is the definition of a function, the proper definition of a function. We do, as we teach these, right? You didn't learn this in college algebra. You learned a provisional and easy to use for the problems you were going to be facing. In a calculus class, it might have upped a little bit, right? But now we're talking about in general for all of mathematics, this definition is solid. And as you teach, you're going to teach one definition dependent upon your students, right? You teach one definition in a middle school that you wouldn't necessarily teach in a high school. And then you'll have a little bit more detailed one in a algebra class versus a calculus class. So even though this you didn't start with this, please understand that this includes all of those other definitions. So let A and B be non-empty sets. A relation between A and B is a subset of A cross B, the Cartesian product of A and B. A set of ordered pairs, A, B, okay, and let S be a relation from A to B. So now we're S being a subset. We say that S is a function from A to B. Given any A in A, there's exactly one element in S whose first entry is A. So there's only one, A goes to one element. It doesn't go to two elements. It goes to a single element. And this means that each input can only have a single output. Okay, it doesn't mean the output won't be repeated. It just means it only has a single output. Okay, notationally. So when does S become F? Why'd we use F? Some of you know. Why do we use F? So if S is a subset of the Cartesian product, and it could include the entire Cartesian product, that's what that means. So some of you may not have taken discrete yet. Some of you might have. So that sideways U with a line underneath of it means S is a subset, but could be the entire set of A cross B. And it's a function. Given any element of A, there's a unique element, A cross B, that's in our subset. And we define the symbol f of A by f of A is equal to B. When we describe the graph of the function in terms of sets, we are really describing the function itself. And instead of calling the function S for subset, we use F for function. First letter, right? That is genuinely the reason. Mathematicians inherently tend to be lazy and tend to use shorthand, which has developed into mathematical notation, instead of writing out everything. Remember that if you've taken the math history and you took it with me, I already know that you know this. If you didn't, you should still know this. Al Khwarizmi's book of balancing that we get and is actually where the word algebra comes from, is a bastardization of his name, um, comes from, was all written in words. It was all words, no symbolic language at all yet. And the symbolic language wouldn't happen until the Renaissance. So, and not everybody was agreed upon then. So don't worry about the notation. Understand what's happening. And then the notation is just shorthand. F was short for function. Concrete to abstract, simple to complex. It's good to keep in mind that learners aren't usually ready to start with the rigorous definition, right? Your students are not ready for that rigorous definition. Can you talk about it? Sure. But you should also have a simpler definition to give them. Maybe what we would call concrete, because it replies to what they're learning in that class. Abstract is what we really are when we talk about mathematics. The new math in the 1950s and 60s confused a lot of kids by trying to start with set theory and build up from there. Why did we have new math in the 1950s and 1960s? Well, if you don't know, or this wasn't covered in your math history, and that's fine, that was when the Cold War was happening. So this is after World War II, and Russia had launched Sputnik, though they were doing stuff before that. Let's not diminish it. They were working towards that goal beforehand. They launched Sputnik, put a man around the earth, and we were like, wait, we need to up the game. So a lot of it was based on the space race, was the push to new math. Um, there has been a new math in your time when they went to more applied problems. That happened, I don't know, 15 years ago-ish, right around there. There is always a new math. It isn't new. None of it's new. It's genuinely just what your emphasis is on. And your emphasis is controlled by the people at your district, the Department of Ed, all of those sort of things. And so there is changes. The changes at the higher level, college, university, those have changed very little, though they still exist, though they're not like big changes like this. There's always new stuff happening in mathematics, though. I know a lot of you think, well, it's mathematics, it's the same as it's been. And that's true in a lot of ways. But there have been new discoveries and new stuff done by uh, amateur mathematicians, professional mathematicians over the past, I don't know, I mean, continuously. It's always happening. So be aware that there's always room for growth, and some of it helps people. You might notice that an algebra book uses y equals mx plus b. This is a form of a equation that people like. It's great for graphing and other things, but they're not talking about them as sets, right? A pre-calc and a college textbook will not use y, they'll use f of x. But is it any different? No. Essentially, these are the same thing. It is being clear that so in the first one, I don't know that it's a function. The first one is a relation, but I don't know for sure it's a function unless I were to graph them all. In the pre-calc or the college algebra, I look at that and I know it's a function because it's using function notation. So again, this is simple to complex, right? We want to give them a piece before we get there. Some people never hear relation in a math class and do just fine. Don't assume they need it. Though, if someone is going into a STEM field and a student asks you a question, you're certainly more than encouraged to explain that there's relations and functions and how they're different. Every uh, function is a relationship. Not every relationship is a function. You guys know that from like geometry. There's certain things that kind of that falls together. Multiple notations. In calculus, the derivative of y equals f of x is y prime, or f prime of x, or dy dx prime, or dy dx, or d dx of f of x. So lots of notation, and I didn't even use the Fluxion notation. Darn, I should put that in there. There's other notations. Sometimes one form is just more convenient than another when we're working with students, also because of where they're at. So keep all of those in mind. Same for function notation. We could write this is all e to the x, right? I could say f of x equals e to the x. I could say x to e to the x. I could use set builder notation. The map of x, y's such that y equals e to the power of x. All of these sort of things are valid. Just one notation might be easier than another. There we go. Okay. So this is one of the first questions you guys have in the written homework. And this exercise illustrates limitations to usefulness of graphs. And that's the goal of this you can kind of see right there. It's telling you what the exercise is supposed to do. And so we're going to consider this function on the reals. And when we say on the reals, we mean it starts in the reals and goes to the reals. So on the reals, um, notationally, it would be f of reals to reals, real numbers to real numbers. This is our function. It is a piecewise function, e to the power of negative 1 over x squared, where x doesn't equal 0 because that's negative 1 over x squared. And if that was 0, we'd have all sorts of problems. And we give it so that at 0, x is equal to 0. So we're done. That's nice. When x equals 0, it is 0. So why is it reasonable to define that? And you need to look at that. You may want to look at mathematically what's happening when you go from the left and when you go from the right. That's always calculus. Remember that, where you would, to find if something existed, you would kind of map that. And in this case, when you map that, it does go to the same place. Though it can't really, that function can't exist at 0. It would be a hole. If it was just the top portion of that function, there would be a hole there. But because we want to make it maybe continuous, we're using that idea. So you can discuss why that would be the case and maybe some examples from a couple on the left, a couple on the right going towards it. And then use technology and construct a table of values for inputs. And the inputs I'm asking for are 0, 0 0.1, 0 0.2, 0 0.4, 3, and 0 0.4. Now, what tool is a good choice for this? You could do this in Excel, but later on you're going to use technology to graph it. So I'm going to already suggest not doing that in Excel because that will not make a nice graph. I'm going to suggest something like Desmos, GeoGebra, Mathematica, any of those that you're used to, whichever that may be. I would suggest using that. If you're using Desmos, you can embed a table there, so that's nice. You can actually click on to put a table in, so that's a good one. Using your answer to B, after you do these, attempt to construct a rough graph over this particular interval. This is a rough graph. This is done by hand. That means on your paper, you're going to have the answer to A. You're going to probably have a screenshot that you printed for B. You're going to have by hand C. What property of the function makes it so difficult to construct a meaningful graph? And you're going to actually give me written explanation of what's the property that makes that challenging. You may remember that as the denominator gets bigger, that number becomes smaller, right? So that may help you. Okay. That sort of logic. And then use technology to graph F. Again, the B is just that table, but you could use that and you could use in Desmos and you could use E and you would do that as a picture, put it in there, but then also discuss those results on what you see. Because when you graph this whole thing from the left and from the right, the maybe from -1 to +1 or -3 to +3, and you look at that, you should be able to discuss what that did and why all of your answers, A, B, C, and D, really kind of make sense. So this is an outline of this one. I'm not giving you the actual work, but I'm giving you an outline so you can finish this up and get this question done as soon as you watch the video. All right. I'm going to do another one for the next little section, and then I'm going to try to do them as we go. Also, though I may not do videos for everything, I will at least post slides. Remember, you can also look at the website that I share in my welcome announcement, not the intro for this last week or for this week that we're in, but the intro for the welcome for the course. I have a link to a website that I keep for this class specifically, also as my general. I think I linked to my general, and you can look at everything that I do. But I will post this video there also, so you guys have access to it. All right, you guys have a wonderful day, and I'll see you next week because of the way the course works. All right. Get up here, pause the recording, or stop it. Yep.